everyone. Today let's talk about session 14.2, line integrals. Last time we talked about what a vector field is. Then our next goal is to have a precise mathematical way to compute how much a vector field is accumulating along a path. This will be done using line integrals. Line integrals can be used to integrate either scalar value function or vector fields along curves. So let's first talk about the scalar line integrals in the plane. So look at this picture on the right hand side. So we have the xy plane, right? We have a surface on top of the xy plane. So let's say this is the surface, okay? And then suppose we have a path on the xy plane, and then if you look at this path and then you look at the cylinder that rises parallel to the z direction, and then you can see this path intersects. So this cylinder intersects the surface, and then it can form a curve f. Okay, so f is this curve, okay? And then C is the curve on the xy plane. So a line integral with respect to the arc length parameter S can be interpreted geometrically as the area under the function f along the curve C as in the picture. We sum up the areas of all the infinitesimally small rectangles formed by f of xy and the ds. So if we look at, you see this blue area, that is the line integral, okay? And if we cut it into small rectangles, and let's look at each of the rectangle. So you can see this rectangle, the base is dx, the height is f of xy, right? So when we sum up the area of the rectangles, we just get the integral along the path C, f of xy ds, okay? So, but in general, if the parameter t is not the arc length parameter, then we have to make a change of the variable. Do you still remember what is arc length parameter? So arc length parameter, we have the property that the derivative of s with respect to t, that equals to the speed, right? So that's v of t, the magnitude of that. Okay, so that's why ds equals the magnitude of t dt. In other words, if we want to use a t as a parameter, let's look at the following formula. Okay, so let f be a continuous function on a region containing a small curve, and here we have a parameterization for the curve. So gamma of t is the parameterization of the curve C on the xy plane. Okay, for a less than equal to t less than equal to b, then the line integral of f equals the integral t from a to b. We have f of x of y, but x and y now are in terms of t, and then we have this guy. Okay, so this is the speed. Well, because we're in the xy plane, so we have two coordinates, right? So what is the speed? The speed is the square root of x prime square plus y prime square. Okay, that is the magnitude, that is the speed, magnitude of the velocity. Okay, let's continue. Alright, some book notation use single line, some books use double line. We can use double line here. Okay, so let's look at the following example. The temperature of the circular plate r equals xy, x squared plus y squared less than or equal to 1 is t of x, y equals, so this is a temperature function on the circular plate. So this is a circle with radius 1 and center at the origin. Find the average temperature along the edge of the plate. Okay, now let's see. First of all, let me ask you. Here we're looking for the average temperature along the edge of the plate. Okay? And I want you to distinguish. Let's look at this. Average temperature on the plate. Do you realize the difference? So here we have the circular disc, right? This with radius 1. Okay, so average temperature along the edge. So we are only looking at the edge of only at the edge of this circle. Okay, so which is the line integral. So we want to measure the cumulative temperature and then over the length of the circle. Okay, so this is only the average temperature along the edge. Now how about the average temperature on the plate? Well, on the plate is on the entire plate, not only the edge. Right? So what will you do in that case? You're gonna let's say this is the region R, right? You're gonna measure the double integral of t on the region R, and then we divide it by the area of R. Now you see the difference? Okay. Now let's calculate. So first, we want to find, in order to calculate the line integral, we need to find a parameterization. What is the natural parameterization for the circle? Okay, so find parameterization for a circle. Wow, the natural parameterization is what? R cosine t, R sine t, but here are the radius 1, so we have cosine t and sine t, right? And then what's next? According to our formula, we also need to find v, right? Which is r prime. Derivative of cosine is minus sine t. Derivative of sine t is cosine t. And then we want to find the speed. Well, speed is sine t squared plus cosine t squared. We know, oh, that is 1, right? So let's see here. So what do we get now? So the line integral is like the t goes from 0 to 2 pi of T is the temperature, but we plug in x equals cosine t. So cosine t squared plus 2 sine t squared times the speed, which is 1, and then dt. Right? This is our formula. So far, so good, everybody? Okay. So let's continue. How do we calculate this? Well, here I can simplify it a little bit by realizing we can move the 100 outside of the integral. And then we have cosine squared. But can you see I can split 2 sine squared as sine squared plus sine squared? But then this guy, cosine squared plus sine squared, is just 1. Okay? And then what is sine squared? Well, here we use double angle formula. Sine squared is 1/2 minus 1/2 cosine 2t. So I hope you're familiar with the double angle formula. Okay, if you still don't remember, let me write it here. Okay, so everybody tell me, what's cosine square? 1/2 plus 1/2 cosine 2t. How about sine square? 1/2 minus 1/2 cosine 2t. The terms are the same, just the middle sign are different. One is plus, one is negative. Okay, now what happened? So we get 100, and then 1 plus 1/2 is 3/2. 3/2 we integrate, we get 3/2 t, and then integral of cosine is sine 2t, but because of the u substitution we divide it by 2, right? 1/2 divided by 2 is 1/4. Evaluate from 0 to 2 pi, so we plug in 2 pi, and when we plug in 0, t0 is gone, and when we plug in 2 pi, we get 4 pi, right? And when we plug in 0, sine 0 is 0. Actually, sine 4 pi is also 0. So the answer is 300 pi. Okay, so this is the line integral. So this is the line integral. How about the length of C? Well, in general, how do you find the length of C? Well, you still do this guy, the integral from 0 to 2 pi, but you don't multiply by the function t. We just find the speed. Okay, find the speed dt. Okay, this is the arc length, right? We talk about that in Calculus II, chapter 10. Okay. All right, but here, because we know this is a circle, so we don't need to integrate it. We know it. What is the circumference of the circle? Well, that's 2 pi r, right? But r is 1. Okay, so which is 2 pi. Then what is the average temperature? What's the average temperature on the edge? Well, that's 300 pi over 2 pi, so that is 150. So far, so good, everybody? Okay, so this is how we find the average temperature along the edge of the plate, where we need the line integrals, and we need to create a parameterization for the curve. Okay, so are you curious to know how to find the average temperature on the plate? So yeah, I also want to show you here so then you can compare both two methods, because sometimes students will get confused in Calc 3 we're dealing with different kinds of integrals, right? We talk about double integrals, triple integrals, and now we talk about line integrals. Okay, so how to find average temperature on the plate? Well, first we want to find the double integral. Okay, so in this case, let's see. It's better to use the polar coordinates. Okay, so let's use the polar coordinates. And then t is 100. Well, here x squared plus 2y squared. You can think of like x squared plus y squared and plus y squared. Okay, so then we have r squared plus r squared sine theta squared. And then we have r dr d theta. So far, so good, everybody. And our theta is from 0 to 2 pi. Our r is from 0 to 1. So this is the double integral. Okay. And then how do we integrate it? First of all, let's distribute the r and let's move the 100 outside. Okay, so we have r cubed plus r cubed sine square dr d theta. Well, then we have 100 integral of r cubed is r to the 4 over 4. And we can think about it like we factor out 1 plus sine square. Okay, and now what happened? R is from 0 to 1 d theta. So which means we plug in 1, that gives us 1 over 4. When we plug in 0, it's gone. And then we compute the integral of 1 plus sine square. But sine square is 1/2 minus 1/2 cosine 2 theta. Right, the double angle formula again. Here we have 25. And then integral of, see, 1 plus 1/2 is 3/2 theta. And then we have 1 over 4 sine 2 theta. Evaluate from 0 to 2 pi. So we get 3 over 2 theta. Theta is 2 pi. But when we plug in 0, it's gone. And sine of 4 pi is 0. Sine 0 is 0. So the answer here is 75 pi. So far, so good, everybody? Okay. Now, how about the area? Area of the region. Well, that is usually the double integral of when the function inside is 1, right? But because now we have a circle, we know how to calculate circle by geometry, then we don't need to worry about the double integral, okay? So that's pi r squared, but that is just pi. So the average temperature on the whole plate equals 75 pi over pi. And we get 75. You see, they're different than the average temperature on the edge of the plate. So far, so good, everybody. So I hope through this example, you can compare the two different questions. First, average temperature along the edge. The other one is average temperature on the whole plate. So you can compare the two different methods. Okay, so when we compute the average temperature of the whole plate, we're working on the double integral, and we don't need a parameterization for the curve. Okay, the boundary of the region. We don't need that. So far, so good, everybody. So if you have questions, feel free to print screen and ask me. Okay, let's continue. Next example. Evaluate the following line integral where c is the curve y equals x squared for 0 less than equal to x less than equal to 1. So first, if we're able to draw the function, then draw it. So what is this guy on the xy plane? Y equals x squared, the parabola, right? And x from 0 to 1. Okay? So this is the portion that we're interested in. Okay? Alright. So in order to compute the line integrals, we need to find a parameterization. And for here we can use the natural parameterization. Okay? So we can use the natural. What is the natural parameterization? Well, here, if y is a function of x, well, then just let x be t, then y is just the function f of t. So here is t squared. And because x is t, then we have the t goes from 0 to 1. So this is a natural parameterization. Well, then next, we want to compute the velocity, which is the derivative of the displacement. That's 1. Derivative of t squared is 2t. Well, then, what is the speed? Well, speed, 1 squared plus 2t squared, so 4t squared, right? Because it's 2t parentheses squared, so that will give us 4t squared. Is that okay, everybody? And now we're ready. Then the line integral equals t from 0 to 1. And then our function x is t, okay? So x is t, y is t squared. And then we have this cube root, and then is the speed, okay, dt. So far so good, everybody? Yes, we're plugging x is t and y equals t squared inside the function f. And you see this guy is t cubed, but we have cube roots, so we only have t. Square root of 1 plus 4t squared dt. What method shall we use? Any guess? Yes, u substitution. Let u be the function inside the square root. Then du is 2 times 4 is 8t dt, but we have we don't have 8t dt, we have t dt. Well, that is 1 over 8 du. Well, 0, so u of 0, u of 1, t dt is 1 over 8 du. Square roots is like u to the 1/2. Wow, how do we integrate? U to the 3/2 over 3 times 2. And then what is u of 0? So we look at this guy, we plug in t is 0, we get 1 plus 0 is 1. U of 1, 1 plus 4 times 1, which is 1 plus 4, which is 5. Okay, oh, this cancel. So we have 1 over 12, and then 5 to the 3/2 minus 1 to the 3/2 is just 1. So this is our answer. Okay, so this is the line integral. So far so good, everybody? Okay, let's continue. So we can use similar idea to extend to R3. Okay, so how do we evaluate scalar line integral in R3? So let f be continuous on a region containing a small smooth curve C. So R, we use the parameterization. Alpha of t, gamma of t equals x of t, y of t, z of t. Now we have 3 coordinates, okay? And then t goes from a to b. Then the line integral equals the integral t from a to b, f of x, y, z in terms of t times the speed, okay? So because we have a curve, now we can measure its speed. So and that is f of x, y, z, and then times, this is the square root of x prime squared plus y prime squared plus z prime squared. So far so good, everybody? All right. So let's look at the following example. So here we are given a parameterization for it, right? And we want to measure the line integral. So start with the parameterization. That's t 2t minus 4t. Oh, do you realize this is actually a line? Yes, because it's all linear terms. And then what is the velocity? 1, 2, minus 4. And then what is the speed? 1 square, 2 square, minus 4 is the same as 4 square. That is 1, 4, 16. Oh, So square root of 21. So far so good, everybody. Then our line integral equals our t goes from 1 to 2 f. So x, we replace x by t, we replace y by 2t, we replace z by minus 4t. And then what is the speed? The speed is square root of 21 dt. Is that okay, everybody? So I forgot to say, remember, before we go over each example, please stop the video and try those examples first. And then after you're done, you continue to play the video and check your answers. Okay, so I hope you already try it. So now let's continue and check our work. Okay, so this is t, this is e to the minus 8t squared. Thanks to that, you see, this is t squared, this is t. What method can we use? Yes, u substitution, right? Let u be minus 8t squared. Du is then minus 16t dt. Then t dt is minus 1 over 16 du. So our integral equals square root of 21, integral u of 1, u of 2. T dt is negative 1 over 16 du. So don't forget the parentheses, otherwise it looks like square root of 21 minus 1 over 16. Okay, and then we have e to the u. Well, e to the u integral is e to the u, and u of 1 was u of 1. But when t is 1, we get minus 8. U of 2, when t is 2, 2 squared is 4. 4 times 8, 32. Right? And what is that? Well, that is minus square root of 21 over 16. We plug in negative 32 minus we plug in negative 8. So we can move the negative inside and then we can switch them. So we have square root of 21 over 16. Now we switch them. So e to the minus 8 minus e to the minus 32. And you know, this guy is bigger, right? This guy is smaller. So our answer will be positive. So far, so good, everybody? Okay. By the way, the line integral can be positive or negative, right? Because let's look at our previous picture. So imagine, let's say, look at this picture. If the f is below the xy plane, then this area will be negative. So it's actually a signed area. Okay? So the line integral could be positive and it could be negative. So far, so good, everybody? Okay, so that is the scalar line integral. In the next video, we're gonna talk about the vector, vector fields along the curves. Okay, so see you soon. Bye.